Hello friends, in the previous videos we have learned about Coulomb's law, and in this video we will be learning few problems based on Coulomb's law and application of electrostatic force. As the beginning, let us see this simple example. A charge of plus 2 microcoulomb is placed at a distance of x is equal to 0, and a charge of minus 32 microcoulomb is placed at a distance of x is equal to 60 centimeter. A third charge minus q is placed on the x-axis such that it experiences no force. The distance of the point from 2 microcoulomb is dash. You should now find out what is the distance of the point where minus q charge is placed such that it will experience no force. Consider this is point where x is equal to 0 and it has at this position is being placed plus 2 microcoulomb. And let us take this is x is equal to 60 centimeter and at this position it is minus 32 microcoulomb. Now you should place a third charge minus q somewhere in between. If you are placing in between plus 2 microcoulomb and minus 32 microcoulomb, then net force cannot be equal to 0. For example, let me take that minus q charge. Say you are placing here minus q charge. This minus 32 microcoulomb of charge will repel with some force F1, and plus 2 microcoulomb, as it is positive, there will be attractive force between these two, and that will be F2. F net will be equal to F1 plus F2, which will not be equal to 0. Therefore, between two unlike charges, we cannot place other charge such that F net on it is 0. You cannot place that particular charge in between them. Then where you need to place that particular charge? So in order to make F net is equal to 0, you can take that minus q charge and you should place it closer to smaller magnitude of charge. Say for example, I am placing this minus q amount of charge at this position, which is at some distance alpha. Now at this position you are placing minus q charge, and because of that there will be two forces experienced by this minus q charge, and that will be one force which is attractive because of plus 2 microcoulomb. Let me take it as F1. And because of minus 32 microcoulomb, there will be a repulsive force in opposite direction. This will be F2. As F1 and F2 are opposite, F net can be equal to 0. Now using Coulomb's law, I will be writing force F1. F1 will be equal to K minus Q into 2 microcoulomb divided by separation alpha square. F2 is equal to K minus Q into minus 32 microcoulomb divided by 60 plus alpha whole square. 60 plus alpha whole square. Now, in order to get F net is equal to 0, you can add these two vectors As a result, F1 plus F2 will be equal to 0. F1 plus F2 should be equal to 0. And in such cases, you will be writing it as F1 minus F2 is equal to 0 because both vectors are in opposite direction. This gives you F1 is equal to F2. Now, substituting the values of F1 and F2 here, A minus Q into 2 microcoulomb divided by alpha square is equal to A minus of minus will become plus Q 32 divided by 60 plus alpha whole square. K, K and Q gets cancelled. Micro gets cancelled. And this will be 2 16ths. Finally, 60 plus alpha divided by alpha whole square is equal to 16. 60 plus alpha divided by alpha is equal to 4. From here, you can calculate alpha is equal to 20 centimeter. That is how, when you are placing a charge minus q at a distance of 20 centimeter from plus 2 microcoulomb, it will have net force 0. Students, let us learn one more example based on Coulomb's law. And in this illustration, there are 3 point charges plus q, minus q and plus q, which are placed at vertices PQR of an equilateral triangle. Here it is plus q charge, here it is minus q charge, here it is plus q charge. They are placed at the vertex of equilateral triangle. You are now supposed to find out force on charge at P due to charges placed at Q and R. Now you should find out force acting at this point. Now let us take here it is minus Q charge, here it is plus Q charge, and here it is plus Q charge. And separation between all the 3 charges are same. I name this as this is P, this is capital Q, and this is capital R. Now you should find the force acting at point P. Now because these 2 charges which are placed at P and R, they are positive, there will be a repulsive force acting in this direction. It will be FER. And one more charge is minus Q placed at position capital Q. As it is positive and this is negative, there will be an attractive force, and this will be FEQ. And magnitude of FEQ is equal to magnitude of FER, because the magnitude of charges and as well as separation is equal. It can be written as K Q square divided by R square. As these two vector magnitudes are equal, you need to find out F net over here. F net will be equal to under root FPR whole square using parallelogram law of vectors, FPQ whole square plus 2 into FPQ into FPR, and angle between these two should be 120 degrees because this is equilateral triangle, it is 60 and this will be 120 degrees. Is cos of 120. This is equal to f p r whole square. It is 1 plus 1 plus 2 cos 120 under root. This gives you f p r whole square. You can bring it out, that is f p r into under root 1 plus 1 is 2, 2 plus 2 into cos 120 will be equal to minus of 1 by 2. And this gets cancelled. 2 minus 1 is equal to 1. This is equal to f p r, which is equal to a q square divided by r square. This is nothing but f as it is given in the problem. So f is equal to 1 by 4 pi epsilon naught q square by r square. The final magnitude which you are getting at position P is f, and this is in which direction? In order to find out the direction, we will be using parallelogram law of vectors. Simply construct a parallelogram. The diagonal gives you resultant, and it is along negative x-axis. So out of all these options, E is the suitable answer. Force F along negative x direction. Students, in this simple example, you have two metal spheres of same mass which are suspended from common point by light insulating string. The length of each string is same. The spheres are given electric charge plus Q and plus 4Q on the other. On one charge, on one mass it is plus Q, and the other it is plus 4Q. Which of the following diagram best shows the resulting position of the spheres? Now we are taking two masses. Here is one mass and here is another mass. This has charge Q and this has charge 4Q, and both are positive. This has mass M and this also has mass M, and both are attached to string. These are attached to the strings. These two are separated by certain distance. Let me take it as x. This length is L and this length is L as it is mentioned. And let me drop one vertical over here, and I treat this angle as theta. So as these two are placed in air medium, and these two charges, for these there will be mass and as well as charge. It is mentioned in the problem. Using free body diagram, you can identify the forces acting upon this charge plus Q. There is gravitational force acting in downward direction, that will be equal to mg, and there is electrostatic force acting outward. As these two charges are positive, there will be a repulsive electrostatic force, and the tension in the string is E. I can take this angle as 90 minus theta. This side, you can resolve this tension into components as E cos of 90 minus theta, and this is resolved as E sine of 90 minus theta. Now, from free body diagram, E sine of 90 minus theta, which is equal to E cos theta, is equal to mg, and E cos of 90 minus theta, which is equal to E sine theta, which is equal to Fe. Fe is electrostatic force. Now taking ratio of these two, E sin theta divided by E cos theta is equal to electrostatic force divided by gravitational force. Sin theta by cos theta will be equal to tan theta. This is equal to Fe divided by mg. So in this problem, it is mentioned that masses of both the charges are equal. Therefore, if you take free body diagram for charge plus q or for charge plus 4q, Fe will be same for both and mg will be same for both. So as a result, the angle over here, this angle and this angle should be same. So that means this angle should also be equal to theta. So as mass of two charges are equal and magnitude of electrostatic force is also equal, and theta should be equal to constant for any charge. So if you take either plus q charge or plus 4q charge, theta should be same. Therefore, theta should be equal. This angle should be equal to this angle. And that is possible only in this figure. So option A is the suitable correct answer. Students, coming to the next problem. A charge of plus q is fixed to each three corners of the square. On the empty corner, the charge capital Q is placed such that there is no net electrostatic force acting on diagonally opposite charge. Find relation between capital Q and small q. So explaining this question, let me take a square. This is A, B, and C, D. At three vertices, at three corners of the square, you are placing charge plus Q. Here it is plus Q, here it is plus Q, and here it is plus Q. And on the other side, there is a charge capital Q placed over, and you should, and it is mentioned that on the diagonally opposite charges, there is no net force acting. Now, using that condition, we will be solving this problem. Now, let us take charge which is placed at position B. On this particular charge, there is force of repulsion because of this charge A, and that will be FAB, which is equal to A Q square divided by each corner. I am considering it as A. This is A square. Between two charges placed at B and C, there is another force FBC, that is FBC is equal to A Q square divided by A square. Magnitude of both the charges are same. Now these two charges are vector quantities. They are perpendicular to each other. As these two charges are perpendicular to each other, the resultant of these two forces should be in this particular direction according to parallelogram law of vectors. And this is FRES. Now F resultant is in that particular direction. F resultant will be equal to A Q square divided by A square whole square plus A Q square divided by A square whole square plus 0 under root. 0 is because cos 90 is 0. This is equal to root 2 a q square divided by a square. This is resultant of two forces acting between charges plus q placed at AB and as well as BC. Let me take this as number 1. Now, along the diagonal, there is another force. Along the diagonal, you are taking plus q charge over here, and between these two, this is the separation between two charges. As this is A and this length is also A, this becomes root 2A, Pythagoras theorem. Now, you can write F E E is equal to A capital Q small q divided by root 2A whole square. This is equation number 2. Now, as capital Q and small q, if we are treating this as these both are positive charges, there will be a repulsive force, and that is in the same direction as that of the resultant force. But what it is mentioned is there should be no net force on diagonally acting charges. That means it is mentioned according to the problem, it is mentioned that there should not be any force along the diagonal charges. Therefore, it is F net is equal to 0. And F net is equal to 0 results FRES plus FED is equal to 0. And this is FRES is equal to minus FBD. Now FRES is root 2 A q square divided by A square. This is equal to minus K capital Q small q divided by 2 times A square. A square, A square, Q, Q, A gets cancelled. Now finally, you can write that root 2 into small q is equal to minus capital Q divided by. So final answer is capital Q is equal to minus of 2 root 2 into small q. This is how you can find out relation between small q and capital Q charge is diagonally opposite to each other. In order to get F net between these two charges 0, you should take this negative, this capital Q charge which you are placing over here should be negative. That is proven in the solution.